So I'm happy to introduce Mr. Jyoti Swarup, guest speaker of the day today. He has completed his mechanical engineering from IIT. He is having close to 48 years of experience, global experience and employment. He has worked in Nuclear Power Corporation India, Engineers India Limited, L&T, Hyundai Offshore Korea, Technic Malaysia, Comprimo Singapore, Shemvagak Shamba Bank Engineering Singapore, Nippon Steel Constructions Indonesia, Emirates National Oil Company Dubai, Gryphon Energy Kuala Lumpur. His expertise includes rotating equipment, piping systems, vibration and noise pressure vessels, heat exchangers and tank farms for refineries, oil terminals, offshore production facilities, FPSO, FSO, and jetties. His expertise in codes includes ASME Section 8, Division 1, 2, and it goes on, British standards, and he has conducted a lot of trainings in Malaysia and Singapore, in plant engineering construction, Singapore, and Dubai, and so on. He's an expert in the field, and we are happy to have him today on this webinar. Uh, like you all, I am also eager to attend this webinar and get to know about more on the piping design and so on. Over to Mr. Jyoti Swarup, please.
Yeah, thank you so much. Thank you for the introduction. I have been conducting the trainings from the time when there were no computer projectors. So I was conducting training 40 years back, when there were only overhead slides. And, we used to write on the slides and basically project it using a projector. So this training on piping design, I mean, it's almost 30 years that I have been doing various trainings in various forums. And I thank IIP for inviting me for this presentation. Now, let me just share my PPT. Give me just 1 minute here. Is it visible now?
You have to make it full screen, sir.
Oh, yeah. Yes, 1 minute. I'll do. Is it correct one? You are seeing single screen, right?
Yes, screen is okay, but you have to make it full screen.
Oh, I made it full screen, that's what I'm trying to say. Any, you don't see it full screen?
Yes.
You are seeing one or two screens?
Two screens we are seeing.
Okay, I have to change it. Yeah. Give me a minute. I understand. I have to just change. So yeah. I am Jyoti Swarup, and we are going to talk about fluid flow piping design today. Uh, I have sent one email to all of you. Today, of course, we should have sent it earlier, giving some kind of a exercise for you to carry out if you can get time, and also what is the input for the exercise and what is the output that you expect from this kind of a webinars. So that exercise could be very useful if you try to do that afterwards. My introduction we have already given, Mr. Prakash, thanks for that. And to talk about, you see, fluid flow. Now we all know, fluid flowing from rivers, from canals, and of course in refineries, in petrochemicals, in water supplies. So what the objective of this whole presentation is to calculate and select appropriate pipe diameter and thickness, connection to equipment based on ports such as 31.3 or 31.1. I have also given a reference if some of you don't have these codes, how you can download from the net. Piping materials to be selected to determine the pump discharge pressure for sizing the pump, which means calculating the line pressure drop. In piping layout, what is suggested pipe support, spacing and how to calculate it, and a simplified flexibility analysis, which means the effect of thermal expansion and pipes as per the codes. So this is how a typical diagram will look like. You have a water source maybe below the ground, then you have a pump, a prime mover, and a water device pump which is pumping it say 1 kilometer away to a building or to a storage tank 25-meter high. So we need to find out that this pipe material, size, capacity, layout, how do we do all that? So this is the objective of this presentation for today. And we will talk about piping. We all have seen piping in our life, water supply from waterworks to our home, drain piping from home, irrigation pipes in farms, cooling water in buildings, firewater piping, and pipes are used to carry pressurized heating fluids, steam engines, etc. And in process plant, process piping system account for significant portion of plant cost as high as 20 to 25%. So piping is a very important component of a process plant and need to be understood and sized most economically. So the most important item of engineering is optimization. That is, you can't select it over what is required or under what is required. So the most optimum size and details of piping system from water tank to a building or a process plant to an equipment, this is the objective of this presentation for today. So parameters are pipe materials and corrosion allowance, design flow rate required, desired flow velocities, pressure available at source and pressure required at final output. They determine pipe diameter and thicknesses. And pipe fittings have pressure losses wherein fluid is traveling over its path from source to destination. And responsibility of a piping engineer includes design and layout, piping flexibility analysis and support system design, pipe rupture restraints and jet shield design, more applicable of process plants, piping around equipment, producing piping bill of material, isometrics, etc., and coordination of piping fabrication contract and interface with other disciplines. So this is the scope of this piping engineer. What are the sizes available? Of course, most of you will know the sizes available in the market. But just to summarize, there are standardized pipe dimensions available defined by OD and thickness or defined by schedules. They are available in the market. You can only install a pipe what is available in the market. You are not going to order a tailor-made pipe unless you have 1,000 kilometers of pipe to be installed. So nobody will make it for you. For plants, you have standard sizes available, which can be from half inch to 12 inch, which are defined based on the nominal size, and the OD is more than the nominal size, and larger sizes 14 inch to 48 inch or 60 inch are defined by the OD itself. So there are two ways of defining the pipes. Up to 12 inches is one method, more than 12 inches is other method. So these are supplied in random lengths 17 to 25 feet or double random length 38 to 48 feet. Nominal pipe size is a dimensionless designation of pipe sizes. Diameter nominal is in metric units. So NPS is in FPS units, DN in metric units. NPS 2 inch OD is 2.375 inches, not 2 inches OD. DN50 is same as NPS 2 inch. And joining methods includes butt welding, socket welding, screwed, bolted flange, quick coupling, etc., etc. So if you see this piping, you see smaller sizes, it's a nominal pipe diameter, and OD is more than NPS. 14 inch and above is NPS, and the OD is shape. So the definitions has to be understood correctly. And what are the thicknesses available in the market? Now they have three different methods of defining the thicknesses. Schedule 10, 20, 30, 40, 50, etc. It is called ANSI schedule numbers, which defines thicknesses. And also for stainless steel, 5S, 10S, 20S, 40S, and 80S. And similarly, the other definition is ASTM or ASME standard, extra strong or double extra strong. And the third method is API 5L defines thicknesses. So these are the different methods of defining the pipe thicknesses, what is available in the market. The pipes can be seamless from piercing solid billets with no welding, or welded type from the plate, roll the plate and weld it, either straight seam or spiral welded, and pipe ends are either plain end, beveled ends, or threaded and coupled. Now, pipe thicknesses usually have a mill tolerance allowed as per code. For carbon steel pipes, is typically plus minus 12.5%. So, if you say a pipe is half inch thick, it does not mean it is exactly half inch thick. It can be half inch plus minus, 12.5%. So, because of the manufacturing tolerances. So, some pipe schedules like Schedule 100 may not be easily available. So, need to use a next higher schedule wherever there is a requirement for the schedule. Now, these are the codes which are for pipe dimensions. 38.1 is for carbon steel pipe and 38.9 is for stainless steel pipe. Sizes from 1 by 8 inch to 80 inches for carbon steel and 1 by 8 inch to 30 inches for stainless steel. Now definitions we have already given how the size is defined based on the OD and ID, and weights can be calculated based on the formula as given here in this slide. I mean, it's just calculating the section area multiplied by the density, and that will give you the weight per unit meter. Now, these kind of tables are available in the codes, which gives you the pipe schedule, thicknesses, and other parameters also can be calculated. For example, in say shell deep or any piping codes, you will find not only the diameter, thicknesses, schedule number, etc., but also inside diameter, outside diameter, metal area, outside area, etc., etc. So a lot of these parameters can be utilized when we need to use it, and we can use those parameters to to define many things like inside surface mass filled with water, movement of inertia, suction modulus, rate of absorption, etc., etc. So now properties can be seen from table or can be calculated from the formula. Now pipe connections are using flanges. Typically, if there is a removable connection, if it is a welding, then it's not a removable connection. And flange ratings are defined as 150 pound, 300, 600, 900, 1500, and 2500 based on the increasing pressure. So if you look at the typical pressure of a carbon steel material, for 150 pounds the pressure is 285 psi. It's not 150 psi. Please understand. Many people think 150 pound flange is 150 psi, which is not correct. So 2500 pound flange rating is 6170 psi design pressure at ambient temperature. And this is defined by a code called ASME B16.5. The dimensions, the size, the ratings are defined in this code, and this code is always required by piping engineer to define the flange characteristics and buy the flanges according to the codes. And then materials have been classified in this code as 1.1, 1.2. Material groups have been classified. So carbon steel is 1.1 and 150 pound flange for a given carbon steel material design pressure at a given temperature, and hydro test is 1.5 times design pressure. So this information is to be referenced from the code of 16.5 for the flanges. Now similar information is also available in valve code, which is V16.34 is a valve code, and it also has another class called 4500 class, which is not a flange, but that is only applicable for valve. So many people confuse thinking that there is a flange rating 4500 pound also, but it is not there. That is for welded pipes. So a lot of such information could be more useful if you actually try the exercises that is shared in the email. Now, larger flanges are defined by different categories and different codes. So 26 is to 68 is by V 16.47 code, and it has classifications like 75 pound also, 150, 300, 600, 900. There are no higher categories of that. And this provides two series, Series A and Series B. Series B is compact flanges, the common is Series A. So these are the definitions which has to be understood by the piping engineer before he can put a particular type of flange into a piping system. Now fittings are definitely required to route the piping because it's never straight. Piping can be all bent, going up, down, left, right, and therefore all kinds of fittings are available in the market. So there can be, bends, there can be teeth, there can be couplings, there can be reducers and teeth and so on and so forth. So all these fittings, dimensions and details are also available in various codes and also available on some of the apps which are available on the mobile. Now we will give you some description of the maps as you go along. Pipe flanges can be defined of various types. So this can be welding neck type, as you can see this figure here. There is welding type, there is welding neck. You have a slip-on type, you just slip it on the pipe and weld it. You have a blind flange, which is a closer. You have a socket welded flange at the end of the pipe. You have a threaded flange, and then you have a left joint flange. So different types of flanges are available. For oil and gas industries, most of the time we use well neck flange, which is the most sturdiest design of these flanges. But any of these can be used depending on the application. For example, in water applications, mostly we use left jointed flanges. The material selection can be depending on type of service, compatibility with other materials, mechanical strength, ductility, elasticity, toughness, need for special inspections, test or quality control, possible misapplication in field, and corrosion and erosion caused by internal fluids or external environment. So there are various types of material that we can select, and some of the material codes available for the American codes are A53 for pipe, A106 for seamless pipes, and so on and so forth. So fittings and flanges, etc., are a lot of materials which are available in the ASTM or the ASME codes, and some of these are only listed here. For pipes, we already discussed ASME 36.1 for carbon steel pipe and 36.19 for stainless steel pipe. API 5L is another code for line pipes. Line pipes is pipelines that you have, cross-country pipelines or long pipelines, wherein API 5L code is used for pipelines with a given thickness. The common material grades available and their minimum yield strength and tensile strength is given in the table below. As you can see here, so API 5L grade A yield strength 30,000 psi, ultimate tensile strength 48,000 psi, and so on and so forth. So 5L grade B 35,000. Now why this information I am listing it here? Because this will tell you what are the strengths of the pipe when you want to do calculation of pipe thicknesses. this information will be required for us. So things like duplex stainless steel 31803, etc., are always available with high strength, yield strength, and tensile can be used to reduce the thickness of the pipe if there is a critical application. The other code that we mentioned was API 5L, which gives the thicknesses, and it does not give, the directly it says X42 grade means 42,000 is the yield strength of the material. So it's like this, we have X80 grade, which is a yield strength is 80,000 psi for the, carbon. These are all carbon steel pipes, not stainless steel. So for pipelines or critical application, we use API grade 60 or grade 65 instead of using a piping grade which is API 5L grade B or A106. So pipelines we always use API 5L pipes, while piping we use ASME 106 or whatever pipe grade that we have. So pipelines can be high strength material ordered to the spec of the client, and of course ordered in bulk sizes. This actual grade may not be available in the market. Now, stainless steel, of course, is used in many critical applications like, pharmaceutical or many chemical applications wherein we use 18 quality or air quality, and used in chemical industry to manufacture equipment for processes. 304L is used in cases where metal is deformed or subjected to thermal loads over extended periods, where there is a heating to temperature between 500 and 900 degrees centigrade. So different criteria is there for material selection, and each of these material is selected. Again coming back to what we said, engineering is optimization. We cannot select a material which is more expensive than required because a plant will become, unviable. So it is always good to select the most optimum material, and we will select only, stainless steel if it is really required, not just because I feel like selecting stainless steel or duplex stainless steel. The choice is always to go with the carbon steel welded pipe, number one. Second is carbon steel seamless pipe, number two. Then comes any other material like copper or brass or bronze or whatever that we have, stainless steel or duplex stainless steel or nickel. But the cost keeps on increasing of this material, and we should only select these materials if it is really required for the project. Now 316 or 316L is definitely more expensive than 304, and definitely 4 or 5 times costly than the carbon steel material. Therefore, the 316L is selected only when there is a real requirement for being a, highly resistant to corrosion. And of course, many clients use 316 or 316L where material exposed to prolonged thermal loads, particularly high temperature 500 to 900 degrees centigrade. So there are different other criteria for material selection, but as I said, always it is always the lowest cost material which need to be selected to optimize the project cost, and not select a size or material which is more than required or less than required. Now this is a typical table from ASME B16.5. I've just copied one of the tables, number 2.1.1, which is same as in 16.34 and 16.5 is same. So for 150 pounds line rating, temperature minus 20 to 100 degrees C, the working pressure is 285 psi, 300 pounds 740 psi, 600 pounds 1480, 900 pounds, and so on and so forth. As I said, 4500 is not for plant, the rest is for plant copied from the B16.5. So these are the pressure ratings for a given temperature of these flange ratings, and that is why, depending on the design pressure of the piping system, you select an appropriate flange for the next higher pressure rating to which the piping system is designed. So this code be 16.5 or 16.34 is important for selection of the flange at the appropriate flange rating and size, and depending on the design temperature that you are designing the whole system for, you have to select the appropriate flange for the maximum pressure rating to which your system is designed higher than that. Now, all this information of sizes and details are available on mobile most of the time, and there are many apps available which can be downloaded from Play Store. And I have given some names here which can be utilized, and I have given the details of some of these in the email that I sent you. That's what all these apps cover. So these apps are very handy for piping engineers to get the piping dimension and the rating data, etc. And any of these apps can be easily downloaded. There are both free versions and paid versions. Free versions are good enough with a little bit of ad which comes, which you have to tolerate. So it gives you all the details. Let us say this app is from, I think, pipe data. It says for 300 point weld neck plan, race tray schedule standard, weight 3.51 kg, bolt weight 1.5, dimensions are marked there, and so on and so forth. So all such information is readily available on your mobile, and for the exercise that I shared, you can use it from the mobile or from the code itself. Both options are available to you to work on. Now coming back to the fluid flow, the other topic, some of you will remember the engineering classes, a equation called Bernoulli theorem of fluid flow. I think we didn't like all this when we were studying in engineering, but this is the fundamental equation for the fluid flow into the piping system that we need to use for calculating the pressure drops and the flow velocities, etc. for the piping system. Now, Bernoulli theorem is based on conservation of energy as total of elevation, pressure head, and velocity at point 1 and 2 considering friction loss may be defined as Z plus P1 by rho 1 plus Vl squared by 2G is equal to Z2 plus P2 by rho 2 plus V2 squared by 2 plus the head loss for the system. So this is the basic equation which is utilized for calculating the pressure loss. HL is the pressure loss for the piping system. So as long as you can find out the elevation of the pipe, the pressure of the pipe, the density of the liquid, velocity, at the 2 points you can calculate the head loss. This is the basic equation. So Z is elevation, P pressure, rho density, V velocity, G is the G 32 feet per second, and HL is the friction. The basic equation utilized for calculation of the piping pressure loss. Now, properties of the pipe will be required for calculation of pressure drop, and a thing called Reynolds number will be one of the important criteria which we will define in the next slide. But viscosity being the most important criteria for calculating the Reynolds number, and it is the readiness of the fluid flow when acted upon by an external force and is temperature dependent. And if you look at this viscosity chart is here, if you say acetone is a very low viscosity, while toothpaste, it doesn't flow. It doesn't flow. Ketchup, chocolate syrup, honey, maple syrup, glycerin, motor oil, liquid oil. So these are different viscosity. Like toothpaste, you can say 300,000 centipoise is the viscosity, while acetone could be, 0.8 as the viscosity. So it's a logarithmic range of viscosity, and you can see very viscous fluid to very fluid, this thing. And this viscosity is an important criteria for calculating the Reynolds number and ultimately the pipe pressure drop. The viscosity depends on the temperature, and as the temperature increases, the viscosity decreases. And this is a typical formula utilized as square equation for calculating the viscosity with temperature. And these ABC parameters can be seen in the tables available into the various publications. Now, a typical Reynolds number is a definition of a non-dimensional parameter called diameter into velocity into density divided by viscosity. So dV rho over mu. At low velocity, the velocity of fluid at center of the pipe is maximum and zero at pipe wall is called laminar flow. As you can see in the diagram above is laminar flow, while at higher velocities is turbulent flow. It's not like this kind of a very smooth flow is there. So you have two things. One is called laminar flow, a Reynolds number less than 2000. Turbulent flow, a Reynolds number more than 4000. These are the definitions of the laminar flow and turbulent flow versus a Reynolds number. And depending on the laminar flow or turbulent flow, the pressure drops into pipe is defined by two different methods. Now, what is hydraulic radius? Hydraulic radius is just the defining of the diameter of a pipe which is non-circular. So, it's the area of flowing fluid divided by the wetted perimeter is called hydraulic radius, and this is what you can use in calculations of the pressure drop in pipes which are non-cylindrical type also. So, this is just information, but details can always be seen in the publication. Now, flow velocity limits. Typically, we use 5 meter per second velocity limit. It's just an arbitrary limit. Somebody say why not 5.5 or 6, but industry normally uses 5 meter per second for liquid at maximum flow rate to minimize flashing ahead of control valve. Also, velocity not less than 1 meter per second to minimize depositions of sand in other solids. Now, this kind of curves are available wherein the flow rate, the liquid flow rate in the meter cube per hour and liquid flow velocity can be calculated from this chart given the pipe size. So, let us say 2-inch schedulative pipe for a 30 meter cube per hour gives you a velocity of around 5 meter per second. So, if you want to limit the velocity to around 5 meter per second, then you can look at your flow rate, you can look at a flow rate, look at this chart and connect a pipe size directly. So if let us say I have a 300 meter cube per hour flow from this chart and I want to limit myself to 5 meter per second, I will have to go with a 6-inch pipe, 6-inch schedule 40 pipe, which gives a velocity less than 5 meter. If I go with a 4-inch pipe, it will give me a velocity more than 5 meter, 11, 12 meter per second, which is not good. So I have to go either 6-inch or 8-inch or 10-inch or 12-inch, smaller than that, if I want to limit myself to 5 meter per second. So I will start with 6 inches. If 6 inches does not satisfy my requirement, I will go with the next higher size. So this is the initial sizing of the pipe that we start with, and then we look at the other details of the pipe sizing. Now, calculation of Reynolds number, I have given here some examples. How exactly? Because many times people make mistakes in units. The viscosity unit has to be dynamic viscosity or kinematic viscosity, and the definitions are different, and the calculation has to be correctly using the example that I have given here using the correct unit. And I have given calculations in both FPS and CDS units. So if you want to work out your Reynolds number in your exercise that we shared, look at the correct units and make sure you get the right numbers, and you can use these examples as your reference documents for your calculation. Now, pipe friction is always there, and the friction is a coefficient called F, and the head loss in the pipe can be defined as F L by D into V square by 2G. So HL is the frictional resistance in pipe, F is the friction coefficient, L is the length of pipe, D is the diameter of pipe, V is the velocity square, G is the acceleration due to drift. So it's a very simple formula. Calculating the friction loss in a pipe depends on the length, velocity, diameter, and a friction coefficient. Now, friction coefficient has been defined by a Moody formula which looks something like this. So, this is a very ancient formula. F is equal to minus 2 log EO 3.7D plus 2.51 by Reynolds number square root of F. So, this F friction factor depends on the F, and you require a iterative calculation to calculate the friction factor using this formula. So, this iterative calculation can be easily programmed into Excel. Of course, nowadays there are other formulas which can be utilized instead of this Moody formula using iterative section. But earlier we used to use only this formula for calculation of friction factor. And as you can see, this is for Reynolds number greater than 4000. For Reynolds number less than 2000, friction factor is nothing but 64 divided by Reynolds number, where epsilon is the surface roughness parameter, which may be typically as given into a next sheet, that will define it. Now, just to continue that what we discussed, there are a lot of approximations available in the in the literature for this equation, and some of them have listed here, like Holland equation or Jan equation or Rigran or Sylvester equation, wherein you don't need an iterative equation that we talked about here, f being a function of f itself. So in this formula, you don't require an iterative calculation. You can use these approximations using these formulas in the computer nowadays. Now, 30 years back, the computers were not available, and that is why we are using the iterative methods of using the friction factor. Now, I've just given a comparison here between various formulas that you can use, and you can see there is not much of a difference, and you can use any of these formulas for your calculation. Now, another approximation of Colby equation by Katemba Melukasvi in 2020 is as below, which is good for computer calculations. And this is what I have given here, which can be easily modeled into your Excel programs. And this is probably a more accurate, formula, because computer, you don't have any issues. Once you program it, you can do very easily, and you can use this equation for your computer modeling of the friction factor. Now, typical roughness of pipe material in a plastic pipe is very smooth. In a steel pipe, is about 46 micrometer. A salt dip cast iron pipe, 122, galvanized iron, 152. And this information is used in calculation of that, friction factor into the friction factor coefficient using the roughness of the pipe material. And this is just a small table available for the use which we can use in our computer modeling of the friction factor calculation. And this is a plot of a Moody friction factors. So for a given Reynolds number and a given roughness, relative roughness epsilon by D, you can calculate the friction factor using this chart. And this chart can be used as a check of the model that you make in your Excel using the calculations using any of these formulas that we talked about. Any of these formulas can be utilized into your Excel sheet and model and then recheck using this kind of a chart, which is available into your any textbook and can be utilized given the Reynolds number and a given epsilon over D ratio. Now, I will just take a small break, maybe 5 minutes, and we will join back after 5 minutes. I will give me about 5 minutes, just drink water and we'll come back to after about another 5 minutes. We can understand in a short course. Yeah. So if you try that exercise, all of you, if you try that exercise, you will get a real feel of what we are talking about in this presentation. And I am available to help you if you find any problem in carrying out that exercise, or if you need that help. You are most welcome to get in touch with me on WhatsApp, on email, or by phone. And I'm offering my services to anybody who is interested in doing that exercise and need help. Now, this is another textbook called Gas Processor Supplier Association, GPSA. They have an engineering data book which is utilized in all the gas facilities all over the world. One of the topmost publications that we have. It Of course this gives the equivalent lengths for valves and fittings for calculating the pipe pressure loss. So as I mentioned about the length is a parameter of pressure loss. So the pipes, fittings and flanges, what we do is we take equivalent length of the each fitting, add it to the straight length and take the calculation for the pressure loss of the piping system. For example, a ball valve, a reduced bore 45D. So diameter of the pipe times 45 is the equivalent length of the ball valve or gate valve or globe valve or band 30, etc. etc. So this table can be utilized for calculating the equivalent hydraulic length of each fitting into pipe system from the source to the destination and add it to the length so that the length can be calculated and pressure drop calculating using the formula that is given here, F L by D V square by 2D. And L is not just the straight pipe length, it also adds up all the fittings equivalent length from this kind of a table. I mean, I've used one code, but there are many other codes which gives you the equivalent length of the fittings and pressure drop. So this is just an example I have worked out here. Let us say 1 kilometer pipeline, 180 meter cube per hour. 200 millimeter diameter pipe, for example, if I take roughness 0.12 millimeter asphalt pipe or zero point 0.5 millimeter of a commercial steel pipe, velocity 1.59 or 2 meter per second, ratio E by D so much, Reynolds number so much, and Moody friction factor calculated or taken from the chart. You calculate friction loss in meter of H2O is 11.62 or 5.5. Now, as you can see, if it's an asphalt pipe, which is very high, roughness of the pipe, then pressure loss is almost double that of a commercial steel pipe. Or if you use a IDP pipe, it will be still lower pressure drop. So pressure drop depends on the pipe roughness. Now, pipe roughness is an important criteria. So, commercial steel pipe or stainless steel pipe, the pressure loss will be relatively lesser compared to a cement pipe or asphalt pipe, which is almost twice. And I have given this calculation method here, which can be utilized as a reference when you do this calculation for the example. Now, what is this head loss? The head loss is nothing but a definition of pressure drop in a piping system that can be calculating using flow parameters by adding equivalent lengths of various fittings into pipe length. And this is an example that I have it here for a 4-inch schedule 45, 600 GPM, surface roughness 048, Reynolds number so and so, pressure drop is 1.81 bar for an equivalent pipe length of 100 meters. The flow velocity is 4.61 per second. So as you can see, the flow velocity is on the higher side. We limit it to 5 meter per second. If it is high side, the pressure drop is very high. Now, this kind of a calculators are also available online, and I have given one of them is here, which can be utilized for calculating the pressure drop. And Of course, there are many others available in the net, but you can use whichever is more convenient to you, and you can recheck your calculation, your manual calculation using this kind of a calculator. Of course, these calculators have its own limitations. Not every calculator gives details of each pipes and fittings. So, understanding of the requirement of the pressure drop calculation is a must before you can use the calculator. Please do not go to calculator directly without doing a manual calculation. My suggestion is don't use calculator to start with. Use calculator only when you understand how the pressure drop is calculated. Now, these are the codes that are available in the market. For example, we talked about two codes, power piping 31.1 or process piping 31.3 in there. But there are many other codes into the ASME system, and it's on fuel gas piping, liquids and slurries, refrigeration piping, gas transmission, gas pipeline, hydrogen pipeline, etc., etc. So this is just a list of the codes in a standard, and depending on the industry that you work on, you can look at the respective code. For example, nowadays the green energy, hydrogen pipeline has a separate code, and they don't use BSME B31.3 as the process piping. So there are many other B31 series of codes which are listed here, but depending on the criticality of your application, you can use whichever code is applicable for your kind of a business. Now today we are going to talk about 31.3, which is the most common code utilized in most of the industry, and probably the basic code that is probably well known all over. And this is how the code looks like. The latest edition is 2022, and it is for refineries, chemicals, pharmaceuticals, textile, cryogenic plants, and related process plants and terminals. It defines requirements for material, design, fabrication, assembly, erection, examination, inspection, and applies for raw, intermediate, and finished chemicals, petroleum products, gas, steam, water, or cryogenic fluids. So this is the most common code, 31.3, and that is why I will be discussing about this code as we proceed further into the presentation. Now 31.3 table of content I have given here, which includes design, material inspection for both metal and non-metallic piping, high pressure piping, high purity piping, etc., etc. And then there are a lot of subsections in each of these subsections, which constitute different types of pipes and gives you details of each type. So this is almost a 500-page document, and you have to look at which section is applicable to your project. So nobody can, probably memorize 500 pages, but there are specific pages available for your industry or your pressure drop or your temperature that you have, and accordingly you select the code and the appendices that you have. So this is a list of appendices which gives you all the allowable stresses and quality factor for piping design, stress tables, and so on and so forth for aluminium, for duplex, for carbon steel, etc., etc. So these codes and the appendices are to be utilized for different applications. So the typical requirements of this code, I'm just giving here very brief. The code is a very large code, but just to give you a few definitions, like fluid service, a general term concerning application of a piping system, considering the combination of fluid properties, operating conditions, and other factors that establish basis for design. Category D fluid services, non-flammable, non-toxic, non-damaging to human tissues, design pressure less than 150 psi, temperature less than 186 degrees. Category M fluid is highly toxic, covered in chapter 8 of the code. Elevated temperature fluid service, metal temperature more than the critical metal temperature of the metal 25 degrees C below identifying the start of time dependent properties. So that's Annex M. High pressure fluid service is again there is a separate section for it. High purity fluid service or ultra high purity fluid service like hygienic or pharmaceutical can use this section, and normal fluid section is the rest of the code. So this code is divided into various categories of fluids, and the correct clause has to be utilized for your industry, whichever you work in. Now, pipe category D fluid service, thermal steel pipe may be used for API 5L pipes, 53 type of pipe or A134 pipe. Clip-on flanges can also be used for category D fluids. As I told, oil and gas we use mostly well neck flanges and not clip-on flanges. So some of these clauses, one of the clauses I picked up was called cold spring. Now what is cold spring? Cold spring is if the temperatures are higher of a particular piping, the pipe will thermally expand and the supports will be unnecessarily loaded with the expansion thermal stresses of the pipe. And those supports have to be designed for a excessive load. So cold spring, what we do is we while installing the pipe, we pull it. We pull it to the 50% of the maximum expectation of the thermal expansion and then leave it pulled like this. So in cold situation, the pipe will remain under tension. In hot situation, pipe will remain under compression, but the stresses will be much lower. So this is what we call as a cold spring. So cold spring is made to reduce the support load, nozzle loads, displacements and stresses in operating mode. But support loads, nozzle loads, displacement and stresses cold mode become higher. So ambient temperature is pipe is stressed, but hot pipe is less stressed. So like this, there are many clauses in the API which can be utilized depending on your case to case basis. And for example, a water piping case, 25-meter high storage tank, water pressure at ground level shall be approximately 2.5 bar. 25 meter is equal to 2.5 bar. Assume carbon steel piping, say 4-inch diameter, over length of 1000 meter with many elbows, walls, strainers, will require a pressure loss of about 1.1 bar or a flow rate of 30 meter cube per hour. Final pressure available is 1.4 bar at ground level. 4-inch pipe will have many outlets to various flats in a building, and pipes can be 1 inch or half inch. And second floor, say 7 meter above ground level, the pressure available will be less than 0.7. So this is how to do further piping sizing and piping pressure drop calculations as we proceed with the piping from the larger side to the final destination, like say in a building. The pipe is distributed all over the flats or all over the colony or all over the city, and pipe sizing can be different depending on how much load we are allocating to each of these sections, and according to the pressure drop will be decided for each section of the pipe. Now, pressure design of piping components requires allowance for the pressure and temperature variation, and we have to design for the worst case scenario. Most severe coincident pressure and temperature will determine the design conditions for calculating the thickness of the piping component. Now, straight pipe thickness can be calculated using the formula which is given in the next section. Then we have to add a corrosion allowance to it, which is based on the life of the plant and expected corrosion. And C can be sum of mechanical allowances like thread depth, loop back, plus corrosion and erosion allowance. And T is the pressure design thickness as calculated from the formula in the next slide. And internal pressure state pipe from code is 34.12, thickness less than D by 6, PD by 2 ACW plus PY is the formula for calculating the pipe thickness, pipe design thickness. So P is the internal design pressure, D is the outside diameter of the pipe, S is allowable stress based on the yield strength and tensile strength, E is the longitudinal weld joint factor. If it is welded pipe, if it is a seamless pipe, E is 1. W is the weld joint strength reduction factor for higher temperature, more than 510 degrees. Y is a coefficient for ferritic steel 0.4, and different materials have different Y coefficient. So you can look at the code accordingly. This calculation is very easy calculation. You have all these numbers and you can calculate the thickness for a given diameter and a given pressure of a pipe. And my suggestion is try the exercise. I'm repeating it again and again. Try that exercise. You will get a real feel of these numbers and how these are calculated. So this code 31.3 gives you allowable stresses for different materials. It's called table A1 or even B for metric. So for different temperatures and different materials, allowable stress value is given here into code, which can be utilized for calculating or using it into the formula which is given in the previous. Now this is I have given an example here for a pipe, 12-inch pipe, 500 psi drain pressure material, 5L grade B ERW, electric resistance welded pipe, 200 degree C, corner allowance 1.8 inch, design as per 31.3. So you can calculate the thickness, add to it corner allowance, and also consider 12.5% mill tolerance. So you calculate the required thickness 0.355 inch, but from the table of the sizing of the pipe, from 355 inch, you see which is the pipe thickness available next to it. So scheduled a standard pipe 12 inch is 0.375 thickness, which is more than required, and I can use scheduled standard pipe, and looking at the weight of the pipe is almost 73 kg per meter. So such apps are also available on the mobile. You can use some of these apps also for calculation. But again, understanding the concept behind the thickness calculation is a must before you go with any of the apps available into your mobile. Now, I have given the same example here for both CGS units and FPS units. And whichever unit your company works on, you can work on, you can use these examples as a reference point for your Excel sheet that you will generate for your calculation. Now, simplified piping flexibility analysis. Now, what is flexibility analysis is, if you have a pipe like this, for example, you have a pipe like this, the pipe will thermally expand if the temperature increases, or even if the temperature does not increase, the fluid inside, the atmospheric temperature increases. Morning temperature is 3 degrees, noon temperature is 52 degrees. So the pipe will expand, and for absorbing the expansion, you create a loop like this. You create a loop wherein the thermal expansion is converted into bending stresses at pipe instead of a compressive stresses. Now, how do we calculate this loop size, what length, what spacing we should have? So, a very simple formula is given in the piping code 31.3, which does not require a software for calculating piping flexibility or the piping stress value. Now, many of you use, complex softwares like Caesar 2 or AutoPipe and all for calculation of the piping flexibility, CI pipe, etc., etc. But 90% of the cases, you do not require to use a software. If you understand the concept behind it, you do not need to use a software for calculating the thermal stresses in a straight pipe or a simplified piping system. And this formula is extremely handy for calculation of the stresses required, of the expansion loops required that is required for absorbing the thermal expansion. Now this formula is dy by L minus U square equal to less than K1. The K1 is a parameter of allowable stress divided by the length modulus. So this formula is outside diameter, E is a reference modulus of elasticity, L developed length of piping between anchors, S allowable displacement stress, which is 1.25 cold stress plus 0.25 hot stress, U anchor distance straight line. So L is the overall length of this pipe, including the loop, and U is the straight length between the two supports. Y is the resultant of total displacement strains millimeter to be absorbed by the piping, and this formula will tell you whether the expansion loop is good enough or not. And I have given an example here how this expansion loop length is being calculated. So given 18 schedule 18 pipe, essay from the code, we already said if the allowable stress tables are available in the code, temperature range 300 to 400 degrees centigrade, expansion is calculated using the expansion coefficient given into the code again. So expansion is almost, the length is 110 meter, and assuming a loop length of say 5 meters, you can see like this. So my total overall length becomes 110 meters. Try to, sorry, oh, sorry. So you can use this formula for calculation whether 5 meters is good enough. So total displacement strain calculated is about 502 millimeter for a 100-meter span. So you can see the pipe will expand by half a meter if there is no expansion loop into the pipe. So you calculate this number. 5 meter found that is more than K1. Therefore, 5 meter loop is not acceptable. Now we work backwards and found the loop of 12 meters is what will be required for satisfying the requirement. And 12 meters is very difficult to physically, put. I think it is got reversed here. Just a minute. I think that the slides is not coming correctly. Eh? Yeah. I think, yeah. No, no, no. Okay, yeah. I think this is the right one. So as you can see here, you may not need one loop, but you may need two loops, each of 6 meters. So this is how we design the pipe expansion loop, and this is very simplified calculation which any of the piping engineer can do himself. He does not have to refer to a code or a stress analysis, software for it for scaling out. And these are the thermal expansion loops designed. There's more details given in some of these codes, how exactly these are to be sized, how the supports in the loops has to be pitched. For example, you can see the support has to be, the guides has to be as close to the loop as possible on both sides of the pipe, and more details you can see, and how much expansion loop and how it will bend and all that need to be detailed when you go into the detailed design of the piping system. Now, piping loops can be various designs also. If you see some of these figures here, in a overhead piping system, you have a three-dimensional loop. Like steam piping, you always find a loop like this because you don't have space to put a very long expansion loop. The space is a criteria. Or expansion loop can even be in an odd shape and not a rectangular shape the way we have designed. And 3D or 2D loops are very common, and many codes and guidelines are available. What kind of a loop can be utilized for our system? Now, what is a piping class? Piping class is nothing but a set of pipes and fittings and flanges into one document, and to for the simplification for the ease of use of the piping engineer. Now, class designations can be ABC as in ONGC, or can be 1, 2, 3, etc. as in shall expect, and providing applicable codes and material selections for pipe fitting, flanges, valves, hose, gut, gaskets, and accessories, and design limits in terms of pressure, temperature, hydrodust pressure, pipe wall thickness. So that means for every pipe, we don't have to design a piping system. We can use these piping classes for a particular pipe. So any pipe, let us say we have a hydrocarbon pipe for a high pressure system, we can use ONDC piping class F1, which is for a 1500 pound rating, flange rating. It gives service type, so which code applicable, sizes from half inch to 16 inch, what is the corrosion allowance that you use, what is the schedule that you use, what pipe material grades you use, fitting grades you use, weld chocolate, flanges, walls, etc., bolting, gaskets, and so on. And then branch details. For example, if you have a T or a header, what shall be the header size, what shall be the branch size, and what are the thicknesses of pipes, etc., that you can use, and the limitations of the piping class. So this is how a piping class is defined. These two sheets together with one piping class. Each client has its own set of piping class. There may be, 200, 300 piping classes for different type of pipes like water application, hydrocarbon, viscous fluids, high temperature fluids, etc. And these piping classes are very handy to piping engineers when designing a piping system. He does not have to do calculation for each and every pipe that he puts in a process plant or a pharmaceutical plant or whichever water plant that we have. Of course, water is very easy that you can have only high pressure and low pressure. The materials are usually carbon steel. But any process plant, there can be various different categories of materials utilized, various sizes utilized, various ratings utilized, and each of these will have a piping line design according to the codes and standards. And this is what can be, I've given a reference here, but I'm sure looking at any of the client documents, you can find the piping class detail into the documentation. Now, another subject that we want to cover, a totally different subject, was piping span calculation. So if you have a pipe supports, for example, if you see the diagram here, the pipe is, there's a weight in the pipe, which can be pipe itself, insulation, it could be wall there in it, and this pipe is supporting. Now, what shall be the span of this pipe? That calculation we need to do when you are supporting the pipe. For example, if you look at this piping here, what is the spacing between support to support? That calculation is again a very simple calculation based on three factors: bending stress, vertical deflection, and the natural frequency. This third one is normally not seen in water piping and all, but this becomes important into critical piping system, especially in hydrocarbon system, driven by reciprocating compressors. The reciprocating compressors operate at low speeds and its frequency may match with the natural frequency of the pipe. Therefore, natural frequency also becomes a criteria in the pipe span selection. And these formulas are given, very simple formulas are available from a book called ROAR. ROAR is a book called Formulas for Stress and Strain. I think many people may have seen it in the engineering studies. And the formulas are: length or the span is equivalent to 8ZSH by W, where L is the allowable piping span, Z is the modular section of pipe we mentioned earlier, S is allowable tensile stress. For example, we can use 3000 psi, or W is the total weight of pipe, which means metal plus content plus insulation. Delta is the allowable deflection, and E is the modulus of elasticity. So limited by stress, limited by deflection, if end condition assumed between simply supported and fixed end at both ends, then formula is slightly different than that. So these kind of a formulas can be seen into the code, into the book I have given here, wrote, and whichever formula is applicable for your case, you can use this formula for calculating the pipe deflections and the stresses, and then work backwards into the span length. For example, I have given here 10-inch schedule standard weight pipe, 400 degree F, A106 grade B material, filled with liquid specific gravity 1.2, insulation 2-inch calcium silicate, maximum deflection allowed 5 by 18. While deflection is a criteria, if you want to empty the plant, your deflected pipe will not empty. So you have to make sure the deflection is less than where you want to empty the pipe and the slope is enough to empty the pipe. So self weight is calculated, content weight is calculated, intense insulation weight is calculated, total weight is so much per feet. Now allowable stress from the code, say for 4000 psi I have taken, section modulus from the tables are calculated, Young's modulus, moment of inertia, and limited by stress is 33 feet, limited by deflection is 34 feet. So you use 33 feet as the maximum span for 10-inch pipes. So this example will help you into calculation the pipe spacing depending on which support spacing that you have or support type you have. Now this kind of tables are available which you can use directly for the support spacing, but understanding of the concept behind it is extremely important. And please do this exercise before you can use this table, as the standard tables have limitations and should not be used blindly without understanding the concept. Now 31.1 has a pipe support span given there. 31.3 does not have. And so I am using 31.1 table here, which is for power piping used in power plants and for a bending stress of 2300 psi. And this is the table given for the support spacing from B31.1. This can be utilized. Then there is another code called MSS SP, which also gives support spacing. So you can use this kind of a tables if you understand the concept behind calculations of the support spacing, and you can utilize these numbers if you have a standard case. But if you have a slightly different case, then you should not use the tables if you can avoid it. Do the calculations. Now, different type of walls are available. Of course, I'm not going into details now because it's a very small presentation that we have. It can be the sizes could be size could be depend on initial cost, replacement cost, labor for downtime, interest leakages, environmental concerns, and types can be flow control, type of wall, material of construction, manufacturer, and it can be gate wall, load wall, quarter ton, check wall, etc., etc. And B16.34 is the code for wall, which can be utilized for depending on the physical dimensions of the wall. So I think this covers my presentation for today. Walls can be a separate presentation altogether. How exactly, what type of wall we've selected, and these are list of codes and standards. I have given here various codes and their latest additions. Now, for a actual case, it's always suggested to use latest edition. For pipes and accessories codes, this is not only SME, the other codes like MSS code or API code for piping inspection, etc. For walls, etc., that code, the real European codes also. And I have also given a list of the Indian codes. Some of the codes for piping and materials, etc., for pipe or steel, etc., tubing. But you can look at the publication that I have referred here for the full list of the codes and standards applicable to the piping and the fitting facilities. So this is the end of my presentation for today. And this is a typical application of a piping system, as you can see, for a crude oil system, for a storage and treatment system, for a natural gas or crude oil storage facilities, you have processing facilities, you have pumps and compressors, you have, transmission lines, you have end users, you have, power plants wherein the oil is supplied, or residential users, or transportation, and piping is an integral part of each of these components that you see in a system. So this ends my program for today, and I'm available for questions if any. I'm stopping the sharing now. and you are most welcome to ask any question that you have.
Thank you so much, sir.
Yeah.